All right, my pre-calc babies, we are back, chapter 6, and we're going to knock out 6364 in the same video. Now, the topic of today is this idea of polar graphs, polar equations, and not a lot of pre-calc professors actually bring this into their curriculum. I do because I teach Calc 1, 2, 3, differential equations, etc. And we call upon polar graphs and polar coordinates in these higher maths. And I want you to at least have a decent understanding of what I mean if you have to venture far enough in your maths to take those courses. So you will be able to, let's assume you were in Calc 2 or Calc 3 and I start babbling on about polar coordinates, and you'll be able to just sit back and relax and say, oh yes, I recall learning about polar coordinates way back in pre-calculus. Okay? So let me start with a question. So let's assume that this scruffy-haired guy here is your professor. And so this is me, and I have dropped my eraser somewhere in the classroom. Now, let's assume that I turn to you and ask the question, where is my eraser? How would you answer? So from the comforts of your desk, how would you answer that question? Well, let's be honest. What would you probably do? You would probably point your finger in the direction of that eraser and probably say something like right there or over there, right? So you would point and then you would say there. Now, notice that when I asked, hey, where's my eraser? Notice that you didn't give me a longitude and a latitude, right? You didn't tell me go over and then up. No, you gave me something different. You gave me a point, right, which is, or when you pointed, which is basically the direction, right? So this is you pointing your finger. You're basically giving me the direction. And you're saying over there, which is a distance. I'll say that one more time. When I asked the question, where's my eraser, you didn't give me the longitude and the latitude of my eraser. In other words, you didn't give me XY points like we use in rectangular coordinate systems. Instead, you pointed your finger and said there, meaning you gave me a direction and you gave me a distance. And if you can understand that little example, then you're going to understand polar coordinates. And the good news is we get to relax a little bit because we're not going to go deep into polar coordinates. It's just another way. It's just a different coordinate system. So let's compare. So when we're talking about the rectangular coordinate system, this is the coordinate system that you have been using the majority of your math career. All the points, well, let's start with the basics. So we have the origin, right? The origin 0, 0. And all of the points that make up this plane consist of an x value and a y value, right? So if you want me to go to point A, you would give me a distance to walk in the x direction, and then you would give me a distance to walk in the y direction, okay? Now, what about the idea of the polar coordinates, right? So let's just say the same point, well, not the same point, I should say, but let's just say we'll call it a point A. But now, and you want to be able to tell me how to get to point A. Well, yes, it is true. You could tell me over x distance, then up y distance. But you could also talk to me about a direction and a distance. So notice that points in rectangular coordinate systems are xy points, whereas points in polar coordinates consist of r theta. So when you graph, you're graphing r's and thetas. But what is r? So r is what I meant when I said distance, right? Well, distance from what? Distance from the pole. So let's talk about r. So I think you and I can, although my eyesight is not great, but I think you can agree with me that I'm on a circle of radius 5, right? So the distance, point A, the distance from point A to the origin, now the origin in polar coordinates is actually called the pole, but the distance is 5. But yet, I think you agree with me, there's a whole lot of points that have a distance of 5. So the particular point that you're interested in, you would also have to give me a direction. And you can give directions by slopes, but you can also give directions by angles, right? Theta. So my eyesight is not quite good enough. That might be 45 degrees, but let's assume that it is. You would tell me to travel a distance of 5 and then rotate 45 degrees to get to point A. Okay, so two different ways of arriving at the same destination. Just one deals with direction and distance, and the other basically just deals with the distance in two directions. Okay, now where do we go from here? So just like when you were first introduced to the rectangular coordinate system, and they probably start plotting points in elementary school, I would assume. But we're going to start there as well. So we're going to start with just plotting points, right? Because remember, this is a cursory glance at polar coordinates and polar equations. We're just going to scratch the surface. And let's start with, how would you plot point P? All right, well, I didn't quite get all of circle with radius 3 inside my little box, but I think we'll be okay. So the idea is that point P is located a distance of 3 from the origin and an angle of pi over 3. So you can imagine, and again, this is I didn't quite capture all of my radius 3 circle here, but you can imagine that that since 3 is positive, the r's, but you can walk a distance of 3, which let's say puts you right here. That's on the radius 3 circle. And now it's time to rotate. Well, do you rotate clockwise or do you rotate counterclockwise? Well, so since pi over 3 is a positive angle, we're going to rotate counterclockwise. So we're going to go this way. And we're going to rotate till we get to pi over 3, which is here. So now I'm at angle pi over 3 and on the circle of radius 3. And that is where point P would lie. Okay? So not bad, right? That's not that bad. All right, so again, notice the graph, though. Notice how the graph looks, the difference between the rectangular coordinate system and the polar coordinate system is the polar coordinate system has all of these concentric circles that are all emanating from the origin, from the pole. All right, well, let's try point Q, if we wanted to graph point Q. Now, it looks like the R value is negative, but the angle is still positive. Okay, so I'm going to travel 1.5, but since R is negative, I'm now going to the left instead of to the right. So I think that would get me to about right here. Does that look about right to you? If it's not, then you'll have to just pretend that that is 1.5. And now it's time to rotate. So, but wait a minute, we got to make sure we understand the direction that we're going to rotate. So since 7 pi over 6 is again a positive, right? So since it's again a positive direction, we would start our rotation in counterclockwise. So we would be rotating this direction. And, well, 7 pi over 6 is about 210 degrees, so that's quite a lot of rotation. And that should get me, quite unfortunate, I can't see the lines as well as I would like to be able to. But I would have to rotate 210 degrees on that circle, which would put me about here. If I could blow that graph up a little bit better, I would probably do a little bit better in plotting that point. But right now, it's just, let's make sure that you can see that we're traveling to the left 1.5, and then it's time to rotate, right? Since it was a positive angle, we need to rotate in a positive direction. We have decided that counterclockwise is the positive direction. All right, now for the last point that we're going to plot, point R, notice that the R value is negative and the theta is negative. Okay, so let's first travel -2. So we're in the R direction, we're going -2. So that puts us out to here. This is the radius 2 circle. And now it's time to rotate 135 degrees. But because theta is negative, right? A negative angle means we're going to rotate clockwise. So we're going this way, right? And we need to rotate an entire 135 degrees, which should put me about here. That actually right there is correct. And that's R. All right, so notice that R, I'm going to go ahead and show you something really quickly, that although the point that we plotted was -2, -135, the point 245 degrees would have put us in the same position, right? So R could be captured as the point 245 degrees or as the point -2, -135 degrees. And the idea is that although the direction, how we got there was different, right? So going to the right 2 and then rotating 45 degrees, if you're thinking about the trajectory of something, this obviously the path that we took to get to point R was different. But point R can be represented with multiple points. All right, so that's the plotting. So what's the next thing you did after you learned how to plot points in a coordinate system? Well, you started, at least at some point in time, you started to plot equations, or in this case, where we started. In this case, we're actually going to start with working our points back and forth between our rectangular to polar equations, and then get to the how would you plot equations, right? So one of the cool things about polar coordinates is the graphs are quite beautiful. You can do a lot more intricate things with polar coordinates than you can with rectangular coordinates. So you get very, very, very beautiful, pretty graphs. So, but nevertheless, let's assume that as of right now, let's assume you don't like polar, right? So the idea would be if you were in your science or engineering classes and they gave you some points in polar form, maybe you would like to be able to get back to rectangular form. Maybe you feel more at home there. Or vice versa, maybe you like the idea of polar coordinates just like I do, and you start off in rectangular and you would like to see what it looks like in polar. So the picture that I have in front of you tells the story about how to get back and forth between these coordinate systems, right? So again, if I label this point A, it doesn't matter. Well, let's say in terms of your arriving at the destination, it doesn't matter if you walk X to the right and then Y in the positive Y direction up to get to A, or if you were to travel a distance of R from the pole and then rotate an angle of theta to get to point A, right? The destination is the same. The process of the steps that you took would obviously be different, but the destination is the same. So let's start with polar. Let's start with polar to rectangular. So we're just going to make use of our trigonometry, our right triangle trigonometry here. So the x value here is simply equal to the hypotenuse, which is r, multiplied by cosine of whatever angle that we're using. The y value is equal to r multiplied by sine of that angle. So let's start there. So let's start from going, the first example, we're asked to go from polar to rectangular. And let's go ahead and do that right now. So in this case, we have an r value, and here's our theta, right? So let me just, for sake of time, so r is equal to 5 for this, and theta is equal to pi over 3. Ready? So you want to get back to rectangular coordinates. So x is equal to r cosine of theta. Let's just plug in. So that would mean x is equal to 5 cosine of pi over 3. All right, well, cosine of pi over 3 is 1/2, so that's 5 times 1/2. Therefore, x is equal to 5 over 2. I'll write that in a different location so it's not so crammed. Therefore, x is equal to 5/2. All right, let's do the same thing with the y value. So y is equal to r sine of theta. That would mean that y is equal to 5 times sine of pi over 3. And sine of pi over 3 is the square root of 3 over 2. So that's 5 times the square root of 3 over 2. Or therefore, y is equal to 5 square roots of 3 over 2. All right, so when you answer these questions, though, we want to answer them as points, right? You were given a point, and you were asked to convert it to a rectangular point. So the form of the answer should be a point. And in this case, it would be 5/2, comma, 5 square roots of 3 over 2. Okay, so let's look at how you would go from rectangular to polar. Well, if you think about the idea of just the Pythagorean relationship between the sides of a right triangle, you can see how r squared is equal to x squared plus y squared, that would mean that r is equal to the square root of x squared plus y squared. Now, your angle, theta, well, if you're given an x and you're given a y, that would mean that you're given the adjacent side, right? And you're given the opposite side. So tan inverse, it works perfectly for converting those side lengths back to an angle. The only caveat is it's always going to be tan inverse of y over x. But the question is, do I have to add pi or not? Well, that really depends on the x value that you're given, right? So you have to think back to the graph of tan. But I don't want to spend a lot of time there. Let's just go ahead and jump in. So the next example, we are given an x value and we're given a y value, right? We're told that x is equal to -8, and we're told that y is equal to -12. And what do we want? Well, we want to go convert that to polar form. So we want our answer to look like this. All right, let's start with r. R is easy. So r is equal to the square root of x squared plus y squared. I know what x is, I know what y is, so let's just plug those in. So r is equal to the square root of -8 squared plus -12 squared. In other words, r is equal to the square root of 208. Notice I'm not rounding, because we want the exact point, just in a different coordinate system. So the square root of 208. All right, now let's find theta. So hold on for a second. Let's follow me up here to how we've defined theta. So the question you should be asking is, well, I know that it's going to be tan inverse of y over x, but is it going to be tan inverse of y over x plus pi or not? And as I mentioned to you, if x is greater than 0, then it's just tan inverse of y over x. But if x is less than 0, if it's a negative number, it's going to be tan inverse of y over x plus pi. So in this case, since obviously our x value is negative, so we're going to have to use the latter of that piecewise, right? So let's go ahead. So this is going to be tan inverse of negative y over x, so -12 over -8 plus pi. All right. So I don't have that calculation. Unfortunately, I don't have my, normally in class I would turn to you and ask you what is that tan inverse of -12 over -8 plus pi. I don't have it. I think it's about, in degrees, I think it's about, well, let me not guess. You can, on your own time, you can figure that out, what the theta should be in degrees or radians. Doesn't matter which one. Just if you're going to do degrees, make sure you change that to plus 180 as opposed to plus pi. Okay, and the last topic for these two sections is how do I convert equations, right? Well, we're going to make use of the exact same equations that were on the previous page, and we're just going to practice converting. We're just going to convert one. We're going to convert a polar to a rectangular. Okay? So our equation is r equals 6 cosine of theta. Right? And what we want is we want the equation of that graph such that we are only using x and y values. All right, so we're going from polar to rectangular, so we just need to make sure we have everything defined properly. So all right, let's see if we can figure this out. So the way I'm going to start this problem is, I know that for example, I know that x is going to be equal to r cosine of theta. I know that y is equal to r sine of theta. So in this case, let me figure out how to work this. So let's start by squaring r, right? So if I multiply both sides of this equation by r, so that would be r squared would be equal to 6 times r times cosine of theta. Okay. And then let's think about, so r squared is equal to 6 times r times cosine of theta. All right, so that would mean, so yeah, because since r squared is equal to x squared plus y squared, so I now know what to plug in for my r squared, right? So this portion right here can simply become x squared plus y squared equals, right? Imagine I'm just plugging in here. And now I need to figure out, how do I rewrite this 6r cosine of theta? All right, well, the r and the cosine of theta, right, this r right here and this cosine of theta, that is the definition of x. X is equal to r cosine of theta. So what you can imagine is I'm just going to substitute x in for r cosine of theta. And what would I be left with? Well, I would be left with 6 times, well, it was 6r cosine of theta, but now since r cosine of theta is the same as x, I can just rewrite this as 6x. All right, so notice at this stage we have succeeded in rewriting the equation without theta, without radius r. We are back to xy form, back to rectangular form. Yes, it is true we could go a little bit farther, we could solve for y, but you get the gist. That was the main goal, was to just get the gist of this material. So I don't think I'll spend a lot more time here. Only thing I want to do is show you some graphs really quickly while we're here. So let's take a look at what the graph of R3 3 cosine of 5 theta looks like. Right? So look at this beautiful graph. In fact, every Valentine's Day, I like to send my wife an equation, a polar equation, and then if I need to change it up a little bit, if she would like more petals on her flowers on this when she plots it, then no problem. I can always just change. Instead of having 5 theta, I can change that to 9 theta. And there we go. Now she has a even prettier flower. And I can continue to play this game. And she can have as many petals as she wants. Don't be stealing my style, by the way. Nevertheless, I just wanted you to see some of your polar coordinates, your polar graphs allow you a lot of freedom to model phenomena, right? So you're not so restricted as you are in rectangular coordinate systems. And as I said in the very beginning, it is fairly intuitive. Direction, distance. All right, I will see you again.